this is a review of the Edgenuity lesson, Exponential Growth. To start off, I just wanted to give you a quick reminder about how exponents work. So anything to the power of 0 is just 1. So it doesn't matter what this base is. 4 to the power of 0, it's 1. X to the power of 0, 1. 12 to the power of 0, 1. And then even numbers like 10,000 to the power of 0, they become 1. Even if you have a negative, if it's inside the parentheses, like this, that whole quantity, negative 3 to the power of 0, that is also a positive 1. For the next part, if you have a value other than 0 in the exponent, it just tells you how many times you multiply the base. So 3 squared, that means 3 times 3, which is 9. 4 cubed, that means 4 times 4 times 4, which is 64. And then this last one, if you have 5 to the first power, that's just 5, because there's only one of them that you're rewriting there. Next, I wanted to talk really quickly about negative exponents. When you're simplifying numbers, you're technically not allowed to have any negative exponents in your answer. So to get rid of them, or to help you simplify, what you can do is if I have 4 to the power of negative 2, if I put a 1 on top of that 4, I can change the exponent to a positive value. So putting a 1 on top changes your exponent to a positive. So 1 over 4 squared is 1, and then 4 times 4 is 16. So like on this one, if I put a 1 on top, 1 over 2 to the first power, which is just a half. The next one, we have 5 to the power of negative 3, so 1 over 5 cubed. And that's 5 times 5 times 5, which is 125. And then lastly, 3 to the power of negative 4, put that 1 on top, so it becomes a positive 4. And 3 times 3 times 3 times 3 is 81. So this 3 to the negative 4th power is the same as 181st. So next, I want to do an example of graphing an exponential growth problem. So I know this is exponential growth because the base is bigger than 1, it's 2. And also the exponent is the variable. So to be exponential growth, the variable has to be in the exponent. And so what I'm going to do is I'm going to make a table. So I'm going to plug in for x, negative 2, negative 1, 0, 1, and 2. My function is 2 to the power of x. And then over here, we'll have the y coordinate that goes with that x coordinate. So when I plug in negative 2, remember you can't have a negative exponent, so I'm going to put a 1 on top. 1 over 2 squared, 2 squared is 4, so we get 1/4, which is 0.25. If you need, I would leave it as a fraction, but if over here on the side you want to say what it is as a decimal to help you with your graphing, that's totally fine. So next value I'm going to plug in is negative 1. Can't have a negative exponent, so I'm going to put a 1 on top. And then 2 to the first power is just 2, so we end up with a half, which is 0.5. And if you want to find out that decimal value, you can use your calculator. You would just go 1 divided by 4, 1 divided by 2. That's how you find those as a decimal value. The next one we're going to plug in 0. So we talked about this. Anything to the power of 0 is 1. 2 to the first power, it's just 2. We only want one of those 2's. 2 squared means 2 times 2, which is 4. So here are x coordinates and here are our y coordinates. Okay. So we have, oops, I guess I should put marks on my x axis. Okay, so our first ordered pair, negative 2, 1/4, negative 1, 1/2, 0, 1, 1, 2, and lastly 2, 4. Okay, so before we connect these dots, I want to talk about what's happening here. As our x value increases, our y value is going to get bigger and bigger and bigger and bigger. Everything doubles here because it's 2 to the power of x. So our next value is going to be up 8, and then 16, then all the way to 32, then 64. So this starts climbing really quickly. So I'm just going to start at the origin, or excuse me, the y-axis, and show what's going to happen. It's going to grow super fast. Now, as we move towards the left, most of the time when we've done lines and stuff, you've just connected them and drawn an arrow. We can't do that here because what happens with exponential growth graphs is they actually never go across the x-axis. Now, the reason that is as we plug in more negative and negative and negative x values, our y value will never become a negative. So as an example, so we've had 0.5, 0.25. Now let's see what happens when we plug in a -3. We're not going to get a negative answer because we had to put a 1 on top and change the 3 to a positive. So it becomes 1/8. So it just gets closer to our x-axis. If we plug in -4, again, we don't get a negative answer. We get 1/16, which is closer to the x-axis. So it never actually goes down below. It cuts off here. It gets super, super, super close to the x-axis, but never actually touches it or goes across it. And what that's called is an asymptote, because it means our graph will not go across this x-axis. And usually it's denoted with a dashed line like that. Okay, so next. What is the what is the rate of change of the functions? So when you're trying to figure out the rate of change for exponential growth graphs, you just pick 2 consecutive y values. So what I mean by that is I wouldn't pick 1/10 and 1/25/2. I would pick 2 that are right next to each other. So let's say I do this one and this one. So what you do is you do the one with the bigger x coordinate, so 1. So I'm going to go 5/2. And I'm going to divide it by the 1 above it, 1/2, because its x coordinate was 0. So bigger x, so you're only looking at the y values, but you choose the one with the bigger x coordinate first. So if we divide those, remember when you divide fractions, keep, change, division, multiplication, and flip the denominator. So that ends up to be 10, if you go straight across, 10/2, which simplifies to 5. So the rate of change here in this function from the table is 5. Similarly, on this one, if we take 2 consecutive y values, we could just go with these 2 right here because it goes 0, 2, 1, 5. Take the bigger one first, so 5, divide it by the smaller y value. So our rate of change here is 5/2, which is also 2.5. Okay, last thing I'm going to talk about for exponential growth is the domain and range of exponential growth functions. So like we said before, I'm just going to make a really rough graph here, a sketch. All exponential growth graph functions grow really, really, really tall to the right and on the left level off at the x-axis. If there are shifts, things will happen, but you're not going to encounter any shifts in this lesson. So the domain, if you recall, that's values that you can plug in for x. And in exponential growth functions, you can plug in anything. X could be 100. It would just be super high up here. X could be -50. It would just be really, really tiny next to the x-axis here. So the domain for all exponential growth functions, for all of them, is all real numbers, which may be written as this as well. Okay. The range, that goes with, so I'm going to put x values here. The range goes with your y values. Now, if you notice, I told you just a second ago that this graph is going to get super, super close to the x-axis. It's crooked, but but never actually cross it. So this line never dips down into the negative y values. It doesn't. It levels off here. So when you have exponential growth functions, the range, the y values are always positive. They're always above the x-axis. So sometimes it's written like this: a set of all values y such that y is greater than 0 is how they usually write it. They may say all positive values, but most often it's like this.